All right. Well, we're extremely pleased to have Huang joining us from Brandeis, and he's going to tell us about Tate's thesis and p-adic strings. Thank you.
So thank you very much, David, for the invitation, and it's my great pleasure to talk here. And so I think a lot of what I'm going to say today probably is very familiar to many of you in the audience, but I hope to bring some new perspectives. And so this is some works with Rebecca, my student, and also my collaborators, and Bogdan Stoica and St. Yao and Xiaozhong. So this is an outline of what I'm going to talk about. I will first review a little bit history of so-called p-adic string theory, and then I will talk about a physics interpretation of Tate's thesis, and then move on to describe a physics interpretation of quadratic reciprocity, and then I'll describe a genus 1 and p-adic string worldsheet action. And then after that, if I have time, I will also mention a proposal for a Lorentzian version of p-adic string worldsheet action. Okay. So let's start with a little bit of history. So the so-called Veneziano amplitude, and it has an interesting history in trying to understand the strong force and in physics, and it's also considered to be the birth of string theory, and then later in bosonic string theory, this amplitude is interpreted as the scattering amplitude of a four tachyon scattering amplitude, and an open string in genus 0. And so after the correct setup in string theory, then eventually this amplitude is given by this explicit integral, where this k1 through k4 are momentum vectors of this 4 tachyon in an R26 with the Minkowski metric. And because 26 is the dimension where bosonic string lives. So yes, this is the amplitude. And then in around 1989, and some physicists, and Witten, and also some others, and including Olsen, they had a remarkable observation. So they observed that this amplitude can be written as 1 over the product of all primes of a similar looking p-adic amplitude, AP. So I'm not sure what's their motivation to care about prime numbers at the time, but they made this a remarkable observation. So so they just observed that if you replace if you just replace R with QP and replace the Archimedean norm over R with the p-adic norm, then you can write down a similar integral, and then they call it AP. And the observation is that this A's have a product formula, but the product formula is needs to be interpreted by analytic continuation. So one can understand this roughly speaking as follows: you look at the functional equation of the Riemann zeta function, and you can write it as a zeta of s over zeta of 1 minus s is equal to this Wiener factor, and then you formally write the ratio on the left hand side as a product over Wiener factors, and then this is what this product formula means. But so here it's just a little bit more complicated than what I described. Okay. So right after their proposal, and Zabrodin, and again in 1989, and he actually realized that their proposal. And so what Zabrodin did was to write down a proposal of a p-adic string, and genus 0 open worldsheet together with an action, and then he computed the scattering amplitude of this 4 tachyon scattering amplitude, and actually the result is exactly what this physics predicted. the AP. So more specifically, as this is very familiar to you, and so take the open-string p-adic worldsheet as the Broussard-Tisse tree for the group PGL2 QP, and then write down an action which I will display, and the tachyons are represented by vertex operator insertions on the boundary of the tree. So what does the boundary mean? I pick an arbitrary vertex in the regular tree, and then I take a cutoff of the tree by a certain radius. Then I insert the vertex operator on the boundary of the cutoff tree, and then I take the radius to infinity, and I compute the limit. Okay. So this is his action, where if AB is the Minkowski metric in R26, and these xi's are functions from the vertex, the set of vertices of the tree to real numbers, and A is just a constant. Okay. So this is the action. And so, as I said, this action actually reproduces the AP, the p-adic, the proposed p-adic Lorentzian amplitude. That's quite remarkable. And in the same paper by Zabrodin, in one of the appendixes, and he also computed that the action on the tree has a dual description in terms of another action on the asymptotic boundary of the tree. And so that he computed by integrating the so-called integrating out the bulk fields on the tree. So the resulting action can be written as follows. So phi is a real scalar field and on the boundary of the tree. Okay, P1 of QP, and then this action. So the action is not local, but you observe that it is conformal in the sense that S is invariant under the obvious action of a PGL2 and QP. So then, for example, this dual action provides you another way to calculate the same four tachyon amplitude, p-adic four tachyon amplitude, by calculating first the Green's function of the dual theory, which I'll explain further. So this same action, I can write it in a slightly different way. So I can write it in terms of this integral, where d1 is a so-called regularized Vladimir derivative, and which actually is defined for all complex number s with a positive real part. And here I just take s equals 1. So for any such s, you can define the operator ds acting on a function in a Broussard space of QP, and by this integral, where this gamma p is the p-adic gamma function, which is the integral of the multiple character times a choice of additive character in the sense of summing over p-adic circles. And so this is a constant. And then this integral converges when the real part of S is greater than 0. So it was known that this operator ds, as defined by this explicit integral, has another can be expressed as the Fourier conjugate of the quasi-character chi-s. So chi-s so parameterizes ds, and then ds can be expressed in this way. And
pseudo-differential operator.
Yeah, exactly. Yeah. So it's by definition a pseudo-differential operator, where f is Fourier transform with respect to the same choice of the additive character defining this gamma vector. So this formula enables you to calculate the Green's function for this pseudo differential operator. Because then you can see that the Green's function is a solution to ds and g equals the direct delta distribution. So at least for generic S, the Green's function then is given by the Fourier transform of the inverse of chi S. So then more recently, around 5 to 10 years ago, this activity got picked up somewhat. So some more generalized theories of this type has been studied, and partially to incorporate fermions and also for other considerations. So this more generalized action has been studied, where so D is parameterized by not just an S complex number, but also possible unitary character tau. So for example, tau you pick it as Hilbert symbol. So this kind of theories have been considered in the literature. And so here the main idea was that you want a p-adic version of the derivative operator, which you can think of in the Fourier space as this multiplicative character taking x to x, which is the absolute value function times the sign character. So we just want to consider a little bit more general case. So let's take a number field f and the non-Archimedean place nu of f. And let's take chi nu to be a quasi-character of local field. So chi nu is this chi s times chi nu tilde, where chi nu tilde is a finite unitary part. Okay. Then assume S has a positive real part. Then we define this Vladimir derivative associated to the choice of my local quasi-character acting on the Broussard space, and by this same formula as before. So
is it still the Fourier transform conjugate of multiplication by chi?
Yeah, I will say in a moment. Yeah. So this integral converges when a real part of S is greater than 0. So it's just a direct generalization of what's been considered before. Yeah, so it's a calculation. So assuming that the real part of S is greater than 0, then we have exactly this formula. So this pseudo differential operator D as defined in the previous page is in the Fourier space. It's just the quasi character.
Symbol.
Yeah, the symbol is chi mu here. Huh?
It's chi quasi character.
Yes, yeah. Right. So this actually has an Archimedean analog. So if you think about the flat and two-dimensional Laplacian operator, then if you raise it to S power, where S is a real number, say between 0 and 1, then you have a similar formula for that operator in terms of such an integral. But that formula, yeah. Yeah. But that formula in the Archimedean place, it diverges when S is equal to 1, because it better be because the integral presentation is non-local, but the Archimedean Laplacian is local operator. But so it has a pole at S equals 1. But it has to be. But here it doesn't have a pole. So in particular, it says that the operator considered previously by Kapsa and others is in fact the p-adic counterpart of the derivative operator in this sense of a pseudo differential operator. So next, let's assume that S is real, and the chi tilde, this unitary part of the character is quadratic. So this is not essential assumption. So you can check that with respect to Hermitian integral pairing, then our D is a self-adjoint. So we consider slightly more general action, which is this. So we have take a complex conjugate of a complex scalar field, right? Then so this is some straightforward statement. So 2-point functions with respect to the quantum field theory defined by this action is then Green's function for this self-adjoint pseudo differential operator D. So this is just standard statement from quantum field theory, which you can adapt to this context. But you need to be careful for some prefactor signs like that. And you can check that the action is real. And then the Green's function is given by the Fourier transform of the inverse of chi nu.
Oh, excuse me.
Yes.
Excuse me. So are you taking the 2-point functions to be Green's functions by definition here?
And you can, but you don't have to. So you can just define the 2-point function as usual by the path integral. Yeah, and then you show that the path integral definition satisfies that D of acting on that gives you the delta distribution.
I see. So, but the path, there is a well-defined path integral, you're saying, yeah?
Yeah. So, yeah, you just take e to the s and e to the is, and then time you have two operator insertions, phi of x, phi of y, and then you divide by the normalization. Yeah. Then
but it's still an infinite dimensional integral, right?
Oh, good question. Yeah. So you still have the usual issue of whether this is rigorously defined in a mathematical sense. Yeah.
No, but is there another way to quantize as
Oh, very good question. So that's a very interesting question, which I hope I have a little time in the end to maybe the thought. Yes.
Just so the integral is over space of complex valued functions on this p-adic variable.
Yes. Okay. Yeah. Okay. So next, it's also very straightforward. We consider all these theories at the local places at the same time. So now, given number field F with a Hecke character chi, then for each place nu, have a local component chi nu as a quasi character locally. Then at each place, you can associate this scalar field theory with this action. Then the 2-point function is given by our Green's function G nu. So the observation is that, so first of all, you have this formula for the Green's function that is given directly by the local function equation of zeta integrals, Tate's thesis. And secondly, actually the global function equation of Tate's thesis implies that this Green's function satisfies this product formula. Again, in the same sense of analytic continuation as we talked in the beginning of the talk. And just think a little bit more. You realize that this global function equation is actually equivalent to this product formula of Green's functions. So there's some examples. Yeah, probably very familiar to you again.
Sorry, could I ask a question again?
Yeah.
When you said that this is equivalent to Tate's thesis, you're saying functional equation for some zeta integrals?
Yes. Yeah. So this formula for the local Green's function, this is equivalent to the local function equation of zeta integrals.
Mm-hmm.
Then this product formula for these Green's functions is then equivalent to the global function equation of zeta integrals.
I see. Thank you.
So, for example, you take f to be q and chi to be this unramified character given by s power of the norm. Then for each p-adic place nu, you have the local Green's function given by this, where you have this gamma p, the local gamma factor. And then at infinity, you have this gamma factor at infinity times this usual norm to s minus 1's power when s is between 0 and 1. So then you can see that this a product formula for the local Green's function in the sense of regularization by a continuation is equivalent to the function equation of the Riemann zeta function in this case. And so the gamma factor has a pole at s equals 1, and the Green's function at this pole can be obtained by extracting the constant term of the Laurent expansion of this Green's function when s is less than 1. Then one can use this to redo Zabrodin's calculation of the p-adic for tachyon amplitude by the Green's function at s equals 1. And so then the calculation is a counterpart of what happens in the Archimedean case. So as another example, you take f to be q adjoint I, then chi is the norm. Then at the complete place, our operator D is the two-dimensional flat Laplacian. And then the theory at the complex place is just the Euclidean 2D free scale field theory. So here the CFT stands for conformal field theory. So then you take f to be q again, and then nu to be p. And you take this local quasi-character, then Green's function is some constant times your Hilbert symbol. Okay, so now I will move on to give a reformulation of quadratic reciprocity under this context. So let's yes. Okay, so let's consider this quadratic extension and the q adjoining square root of d, where d is this familiar guy, where q is an odd prime. So we don't have to consider this extension, but this is one that simplest one you can consider to think about quadratic reciprocity. So among finite places, it's only ramified at q, and it's purely imaginary if q is congruent to 3 mod 4. So a remark is that Flint and Witten actually considered a version of the product formula of a 4 tachyon scattering amplitude also for closed strings. And then for closed strings, they discovered that you need to use this quadratic imaginary field in order to state the product formula. So now let's consider this family of unramified characters on K, given by this S power of the norm, and S is real number between 0 and 1. Then again, for each local place nu of K, we have a scalar field theory specified by the local component chi nu. So here's a formulation of quadratic reciprocity, which is in this context. So it's formulated in a physics-friendly way. So the formulation states that there exists a finite Hackett character chi nu tilde, such that for any place P of Q and any two rational numbers x and y, which are not equal, and s between 0 and 1, one has this equation. So on the left is product of all over all places nu above P in K. So remember, our Green's function are defined locally. So we have three parameters for the Green's function. One is the choice of our field, of a number field k. And then the other is a choice of a place of k. And then the third piece of data is a choice of a local quasi-character and a place. Okay. So on the left side, it's just the product of these Green's functions with respect to this data, and multiply over all places about p.
Sorry, can I, the scalar field theory. So each of these Green's functions is a function for a scalar field theory. The fields are what? They're functions on QP or on the completion of K. I mean, what are the fields in this local field? They're functions.
They are complex value functions on QP.
It's always on.
On the local field. Yeah.
So the scalar field on QP, but the action is determined by the character of some extension. The Hackett character on some.
Sorry. So the scalar fields are functions on the local field.
On the completion of.
Yeah.
Okay. So
Yeah. So on the right side is, again, roughly speaking, it's a product of these local Green's functions. So the first piece is just the Green's function with respect to Q and the place P and the chi-s, and the second is roughly almost the same, except that you have a twist by this unitary character. And then you divide by chi tilde of x minus y by some obvious symmetry reasons, by swapping x and y. So it might look strange at first sight, but you will see the moment that is actually is equivalent to quadratic reciprocity. So the local gamma factor, recall that it's a ratio of local zeta factors multiplied by an epsilon factor. Then, if you assume this statement, then you can deduce that the chi tilde in this case has to be the unique non-trivial quadratic Dirichlet character with conductor Q, given by the quadratic symbol, by just looking at function equations of that kind zeta function and Dirichlet L functions. Then at a finite odd prime P not equal to Q, then you can check that the identity is equivalent to this equality. And at the place 2, the identity is equivalent to the subdimensional. Yes, although it's very familiar, so let's just do an example. So our Green's function G is equal to the local gamma factor times this chi nu times chi1 inverse. And then the gamma factor is the epsilon factor times this local L ratio. So for example, if you take this quadratic extension by joining root of -7 to Q, and take P to be 3, then 3 is inert in the quadratic extension. Well, that's the same. That's equivalent to saying that this the joint symbol is -1 by Hensel's lemma. So the left-hand side, we have only one factor because there's only one, because 3 is inert. So this factor is Green's function that is given by this, and now this local L factor is this one. So it's a product, and then we have the chi tilde is the unique quadratic Dirichlet character with conductor Q. So on the right side we have two factors. One is this one without any twist, and the other is that one with the twist by this quadratic character. So then you can see that the equality of a product of Green's functions in this case is equivalent to this statement, that these two symbols are equal. So this generalizes to all the odd primes P, and for the case P equals 2, the identity is equivalent to that one. I've got a bracket here, as Hensel lemma works slightly differently at this place. So what happens at the Archimedean place? So when Q is congruent to 1 mod 4, the equality is just trivial. But when Q is congruent to 3 mod 4, then we have a quadratic imaginary field. Then the left-hand side Green's function is equal to this. This is the Euler factor, and then the right-hand side is again a product of two Green's functions. So we have this and the two ratios, and then you see that the equality holds and is equivalent to the duplication formula for the gamma function. And for the case when P equals Q, so in the ramified place, you can calculate, and in this case, the identity just holds. So you can calculate by calculating the local epsilon factor. Okay, so this is a statement of quadratic reciprocity that is stated in a more physical way. So the next goal is try to actually physically derive this reformulation of the quadratic reciprocity. So first, let's consider the theory at Archimedean place, and for a quadratic imaginary extension. So at Archimedean place, the 2D free scalar field theory. So we have this, and if S equal 1, then the theory is conformal, and the action is invariant, and the two commuting copies of the Witt algebra, holomorphic and anti-holomorphic. But when you deform away from S equal 1, then you have a long local action, and given by this. And then a remark is that these deformations are actually closely related to the so-called dimensional regularization used a lot in particle physics, actual computations. So dimensional regularization was first proposed to regularize some divergent integral by changing the dimension of space-time. But then it was realized there was a mathematically rigorous way to do this. So instead of changing the dimension of the space-time, you modify the propagator by raising the propagator to a power, which the power is a parameter. Then when the power has a big enough real part, then the integral converges, and then you identity continuate the integral to the power you are interested in. But you have a pole at the power you are interested in, and then you do the same familiar business of do the round series expansion around the pole and take the constant term as your definition of the integral. But then you get ambiguity from the definition because the local expansion parameter is non-canonical. So you have ambiguity coming from the poles. But then you eliminate this ambiguity by the group of renormalizations. So this is, I think this is a way to mathematically understand what was going on in dimensional regularization. But such a modified propagator is actually a Green's function to exactly such non-local operators. So these non-local deformations are actually hidden behind a dimensional regularization. So it's not something, so it's actually something familiar. So the deformed family of theories no longer respect local conformal symmetry. So in other words, the Witt symmetry is broken. However, for OS, it turns out that the global conformal symmetry still leaves the action invariant. So statement is as follows. So you consider the deformed action by the S power of the Laplacian, and then you can check that the action is invariant under this action of SL2C. So the action is deformed by this parameter H, and H is 1 minus S over 2. And likewise, S is also invariant under an anti-holomorphic copy of SL2C. And these two actions commute. And you could try and see if the action is also invariant under operate under vector fields that have possible poles at 0 and infinity. For example, c to the 3 partial, and maybe some deformation of that, and it turns out that certain terms won't cancel unless s equals 1. So the full width algebra is broken at s less than 1, but the SL2C remains. So then this global conformal symmetry actually leads to a holomorphic factorization of our field phi. So so this, I think, familiar in the conformal field theory literature. You take an expansion of the conformal of the field phi, and then you can read off the representation of the two copies of SL2C on the coefficient operators, and from the definition here. And then you see that the representation is an external tensor product of this irreducible representation, which is this one, the Casimir X by this 4h times h minus 1 plus 1. So this structure forces a holomorphic factorization of the field phi, and this factorization is then responsible for the Green's function identity. So recall, in this case, the Green's function identity is actually a factorization of the Green's function at the complex place is equal to the product of two Green's functions at a real place. And the argument breaks down again when x equals 1, because then the representation stops to be irreducible. But then the symmetry gets suddenly enlarged to a Virasoro algebra. Okay, so maybe skip that. So now what happens at non-Archimedean place? So this is not finished yet, but so net f to be sorry, so notation is a bit messy here, and so I use f to denote a local field and characteristic 0. Then we consider a central extension of GL to f by so as a set is a set of tuples g and epsilon, where epsilon is a choice of a square root of the chi-tilde unitary character of a determinant of g, where g is an element in GL to f. Then we can consider this action of g tilde on our field phi. So this is actually something familiar. So if you look at the complex place, and then you write this action in terms of the Lie algebra, then you see it's something familiar. It's just a definition of a quasi-primary field. So this is just a more general version of a definition of quasi-primary field that works for all the places. Then here's something you can calculate. When s is between 0 and 1, then our deformed action s is invariant under this action of g tilde. And the proof is again some calculation, and where you use again the local function equation with zeta integrals. So the hope is that this will lead to a physics derivation of this Green's function product identity, which is equivalent to the quadratic reciprocity. And the main observation is because the theory is defined here has both conformal symmetry, and is also, if you pick the character to be unramified, so the character defining D to be unramified, then the action is also invariant under the Galois group. And okay, so another thing that is not written is that this formulation has a straightforward way to be generalized to, I think, at least abelian extensions. Yes.
Is there a physics interpretation where the product formula should come from? So you have an interpretation at each time of this field theory.
Yes.
Is there kind of an intuition of why there should be a product formula locally?
Yeah, that's a good question. I don't understand that actually. So so at the very beginning of the subject, there's this observation that the four-tachyon amplitude has a product formula. I think it's a very remarkable observation. I still don't understand why you have such a product formula. But the Green's function is much simpler object. And of course, I think that the most naive intuition of physics is that if you have a quantity that is, for example, a rational number, you expect such a product formula. But this is probably too naive because the five-tachyon scattering amplitude doesn't have a simple product formula. Yeah.
You said the product formula followed from functional equations, right?
Yes. Yeah. Right. Yeah. The product formula for the tachyon for tachyon scattering and this Green's function and product formula, they both follow from functional equations.
Yeah. So you could ask for a physics interpretation of the functional equation, I guess.
Yeah. So I think we don't know when should we expect such a product formula in the physics, and I don't know about that. So now let's talk about what happens in genus 1. So it has been open question to find a higher genus p-adic string worldsheet action. So let's take the Tate curve, QP star mod q to the z with q with norm less than 1. Then a complex valued scalar field on the Tate curve can be put back to a periodic function phi on QP star. Then can write down this action. The action looks very similar to the genus 0 action. But here I use the multiplicative power measure because I'm dealing with the Tate curve. And then S is just a fundamental domain of the quotient map from QP star to Tate curve. And then D is defined almost the same as before as well, but the only difference is, again, I changed the integral domain and from all of a QP and a QP star to a fundamental domain. Okay, so I have a factor of x norm here, which would cancel with another factor of 1 over norm of x because if you switch from the multiple measure to the additive measure. So let's take, for example, Q to be a p to the m. Then take S to be the disjoint union of these p-adic circles. Then the action is independent of the choice of the fundamental domain. And the remark is that there is, again, a family of deformations of D, similar to the genus 0 case, as long as you have the correct action of the global conformal group on the phi, as we described.
Sure. When you say independent of S is the section, right?
Yeah.
Yeah.
Yeah,
S is
so
also the action, so the notation is confusing.
Oh yeah, so sorry, 2S. I should probably switch from this S to something like A. Yeah, sorry about that. Yeah, I was writing with my toddlers. Okay. And so yeah, so again, to understand the physics, it's crucial to understand the operator D, and D so it's self-adjoint, negative and semi-definite, and it preserves locally constant functions, which you can verify. So here is it's easier than the Archimedean case here, because you can filter the space of fields by finite dimensional vector spaces of functions that descend to the quotient, such that the conductor is bounded by some number k. Okay, so, or equivalently, you can consider projections to finite quotients, and consider only functions that pull back of functions from finite quotients. So, or you can say as this is a filtration by functions depending only up to the first k-1 p-adic decimal digits. And so this gives you a filtration. The filtration corresponds to truncation in the physics terminology. So it's nothing but truncating the quotient graph of the tree by the finite group gamma that is generated by this element, and truncation up to a radius k. So this is the familiar truncation used by Zabrodin, but now adapted to the quotient by gamma. So again, we want to calculate the Green's function. So for each k, the Green's function is then a solution to this finite dimensional matrix equation, where delta is the direct delta distribution and v is the norm of the section, and j is just constant one function. And then, as usual, you can show that up to a constant, adding a constant function, there is a unique symmetric Green's function. So one thing I want to mention here is that it's interesting to consider the Archimedean counterpart of this, which is the Green's function on the complex torus and with respect to the flat Laplacian. So that object, I think about 10 years ago, and there was a very interesting paper by Huang and Chang Shouning that proved that Green's function has either 3 critical points or 5 critical points, and depending on the moduli. And the 3 critical points always is just a result of this reflection symmetry. And here it's easy to see that the p-adic Green's function has this reflection symmetry just by observing from the definition in terms of integral. And furthermore, this is a technical lemma, which is not very important actually for our purpose. So fix any y, then the Green's function depends on the difference of x and y only up to certain leading p-adic digit. So then by using these observations, you can prove that our Green's function exists. So you can prove it by considering the projections, pi k from the bigger quotient to a smaller quotient, and then you have an integration along the fiber, and then it takes a symmetric Green's function to a symmetric Green's function, and then you use this to prove that the limit as k approaches infinity exists, and this gives you the Green's function. So because of this, you can actually do numerical experiments and study the asymptotics of the Green's function near the diagonal. And this is how we arrived at this solution. So when p equals to the special case, when p equals to m equals 1. So remember, m is the parameter of the Tate curve. So q is equal to p to the m in this case. So when m is 1, p is 2, you have this formula for the Green's function. So it starts with the log singularity, and then you have corrections by these powers of norms. So in fact, if you look at it, it's actually a counterpart of the Archimedean case. So the Archimedean case also starts with the norm, and then you have a correction. The first correction is proportional to x minus y norm squared, where the real respect to the real norm. So yeah, but I think interesting thing is here that our p-adic p is not even a local operator. So I don't know if there's any a priori reason to expect that the Green's function has this structure. So when p is 2, m is 2 is slightly more complicated. So here you just modify from x minus y, the norm of that by this simple thing. You divide by the max of normal x, normal y. Then you have the Green's function is still it's the main body of Green's function is still the same as the previous case, but you have a correction that depends on x, y, only up to their norms. Okay. And this is what happens in general. So for general P and M, you have the Green's function is given by such a power series plus a correction that can be easily computed that only depends on the norms and x and y. And then the power series, you can explicitly compute. This is the coefficients. So in the Archimedean case, this Green's function can be packaged by one of the Jacobi theta function. But in the non-Archimedean case, it's I don't know if there are formulas like that. But indeed, Christian Jepson observed that it has a closed formula in terms of Q digamma function, which is a log derivative of the Q gamma function for Q equals P. Nice. Yeah, so finally, let me just briefly mention so this is related to the question at the very beginning. Think about quantization of the p-adic worldsheet action. So here's an idea to define a Lorentzian p-adic worldsheet action. So phi again is a scalar field on QP, and so my dt is supposed to be an analog of a partial t squared in this situation. So it's defined to be the graph Laplacian along the radial time direction. And then du is supposed to be an analog of a second order partial derivative along the spatial slice. And at this stage, I think these details I'm not sure which exact function space do I want. Yeah. So, but
No, excuse me.
Yes.
When you're considering this action, is this still under elliptic curve or?
No, it's just it's still a genus zero action.
Just genus zero. Okay, that's
yes, yeah. But I think you can write down the same action on the quotient and on the Tate curve. So the equation of motion is then the familiar one, as you can now work out. And then this can be solved by separation variables. And then on the unit circle, which is regarded as a time slice of the p-adic string, then you can check that quasi characters are eigenfunctions of this orbital du. So this is very similar to what happens in the Archimedean string theory, where the string states are constructed from Fourier modes on the time slice. Yeah, so this is an attempt of it. Yeah, I think I will stop here. Thank you.
Questions?
Sorry, in the previous formula, what are you calling the radial time direction? I didn't quite understand.
Oh, that's because, for example, for the usual closed string, if you think of a propagation of a free string from time negative infinity to plus infinity, it traces out a cylinder. So you consider conformal map by the exponential function. Yeah, it's exactly this picture.
I see. Yeah.
Ask, there was these papers of Witten from 88 or so, that this free fermions on an algebraic curve. And then there's, I guess, more work of like Tate more recently about this. So it's somehow where he interprets these kind of product. I mean, he has an analog. He notices some parallel between this kind of product formulas and quadratic reciprocity specifically, and kind of word identities for conformal field theory on a Riemann surface. And so he had, there's some kind of interpretation there of a product formula. I think it's something like a global central extension, a central extension splitting globally, which has a local one. So it would be really, really interesting if somehow to take, so, you know, Witten took quadratic reciprocity and had a CFT analog, and now you're doing, it would be really interesting if you could somehow take his physics arguments there on a Riemann surface and see I mean, if, I don't know, to just kind of direct that in a number field, that somehow there's some kind of word identities associated to a number field that tell you this product formula or something like that. But
Yeah, definitely. I think I know what you're talking about. I tried to understand that paper, and unfortunately I didn't have a good understanding.
Yeah.
And also that I think maybe that paper concerns more function field and
yeah,
but
yeah. So, but there should be some analogy.
yeah, that's a remarkable paper.
I'd love to understand.
Yeah.
Okay, I guess it would, another direction that would be really interesting is if you can replace Hecke characters by automorphic functions on
Yes.
other groups. If there's some version of field theory where automorphic function somehow gives you some kind of field theory, the action of the field theories.
Yes, definitely. Yeah.
Did anything happen this week?
I don't know. I don't know.
Yeah, but oh no, there's no. I mean, I'm just saying. I'm just saying Hecke characters in GL1 automorphic formula. What happens for GLM? When you do a field theory where the
Actually, I have a paper with the GO1 integration in the GOM alpha. Yeah, so in other words, you replace Tate test function by more general function, and then same Tate integral produce the function.
Yeah, let's talk about that tomorrow. Let's talk about that tomorrow, maybe.
very exciting. Well, thank you very much.
Thank you.